that's my son. He's 7 minutes away at my home. That's one of the good things of having a conference right on campus. It's awesome to roll out of bed and then come and give a talk. All right, so let's see if I'm going to break my computer somehow today. All right, so it's an honor to be here and to tell you a little bit about our work, particularly because our audience here is so diverse. I thought I'd give a couple stories of the kind of materials that we work on and how they could be relevant for medical applications. So one of the things that we do is, and you notice that I'm trying to get the laser pointer somewhere and I can't even find where it is. So this is a digital laser pointers which have their own problems. It's weird. Oh, there we go. Woohoo! So these are my conflicts, basically I came here a year and a half ago because I thought this place has a lot of really interesting opportunities. And the kind of work that we do is very diverse. It kind of ranges everything from devices to materials to very biological things. But there is a common theme, and the common theme is that we do try to create therapeutics that address the needs of an individual patient. So I'll give you some examples of this. So I'm going to give one example of a material today that's kind of medically relevant and is used for addressing patient needs. We do a lot of work on devices, so we have a strong device connection at this meeting. We work on things like flexible, theranostic devices that can sense and release drugs as needed. We work a lot on regenerative medicine and taking cells and directing their behavior in the ways that allows us to generate therapeutics, cell-based applications such as personalized stem cells or personalized immune cells for things like cancer, and a bunch of things related to fabrication of materials, particularly biologically friendly materials using technologies like bioprinting and scaffold formation, and trying to build tissues on a dish to be able to mimic things like human physiology. So for today, I'm going to give a couple examples. One is an example of a biomaterial, and then the other one is some of our 3D printing work on trying to enable building biological tissues using these technologies. So, and of course, all of that is built because we work in very big teams. So the first example I want to give is an example of a shear thinning material that we've been using for medical applications. So this is, the idea here is how do we actually generate materials that can be directly injected into the body through catheters or needles. And once they're inside the body, they can perform a particular kind of functionality. So, so this is what the general idea is. So let me talk to you about the medical problem. So hopefully this video will work and we can talk a little bit about what the issue is.
Dr. Tara Narula joins us at the table to discuss. Tara, I think most people hadn't even heard of this procedure until yesterday. So what is it exactly and how do you discover it?
An embolization is a procedure we've had since the 1970s, and basically the idea is to cut off the blood supply to a lesion in order to shrink it or to prevent bleeding. And so what we do is we take a catheter, which is a very tiny small tube, almost spaghetti size. It goes up through an artery in the groin, into the aorta, and then into one of the renal arteries, the artery that supplies blood to the kidney. You then find the smaller artery that's supplying blood to that particular lesion, and through the catheter you inject some sort of material, particles, a gel form or coil, that essentially closes that blood vessel off so no blood oxygen or nutrients can get to the lesion, it shrinks.
So that's the kind of procedures that we've been interested in dealing with, these things like embolization. And embolization is a big field. There's many diseases where you actually want to cut off the blood supply. These include things like, of course, tumors, where you want to prevent the tumors from growing and metastasizing. Things like aneurysms and internal bleeding, whether they're in the brain or peripheral application, and many other types of things. So what's the current procedure? So I spent many years as an engineer in the hospital. So what I got exposed to are a lot of these clinical problems. So this is a types of things, problems that people have, where this is the blood vessel, there's a weakening of the blood vessel, and then you get this bulges called aneurysms that can burst internally and even cause death. Now, what people do, what clinicians do to treat this is that they can use these metallic coils with the idea that you can put them in place and then they slow down the bleeding, the blood flow, so that the blood forms a blood clot. And this is a real example where you can see the catheter, and there's been many coils that have been deposited here, dozens and dozens of coils to try to prevent the internal bleeding from happening. Now, what does this require? It requires one for the coil to go to a place and then to induce blood clot formation. Now, in many cases, this is not workable. So, for example, here's an example of an internal bleed of the gastrointestinal tract. And the clinician here has put many of these coils here. But if you put the contrast upstream and look at the blood flow, you see that the blood goes right through. So the coils have not worked. And this happens because a lot of times people are on anticoagulant medication, like warfarin and other things. And there's other issues like if you're already been in a trauma, in an accident, you already have lost the ability to form blood clot because you've lost a lot of blood. So how do we address this? I started working with a clinician friend of mine a while back on trying to design a biomaterial that can be used to address this issue. And this is a material that is shear thinning. It's made from fairly biocompatible materials, gelatin and laponite, which is a cylindrical nanoclay that's used a lot in a lot of products like your toothpaste and many other kinds of kind of pharmaceutical and healthcare related products. So when you mix these two different components together, what you get are shear thinning materials because there's a lot of electrostatic charges between these two different components that allows the bonds to be formed when there's no physical force. But when you apply a particular level of physical force, things break and the whole material flows like toothpaste. So, and the other thing about this material is that it's a family of material because obviously you can change the ratio of these two. And also you can change the overall concentration of your material in the solution. So you can get potentially a range of different properties. So here I've kind of shown some nomenclature that we use. So this is just the fraction of the nanoclay that is used in the material. And you can see some images of it flowing through a needle or being held between two cuvettes, maintaining this shape or other types of features. Now, when you look at the mechanical properties of these materials, you see that they're very tunable. So you can actually change the material properties and the resulting yield stress, the amount of force you need to make it flow, by changing the concentration of the material, that's this nanoclay materials, or the overall solid content of the gels. And if you look at it, you get things that are fairly strong and fairly weak depending on these properties. The other thing is that these are reversible properties, so if you apply the force, the material becomes liquid-like, and when you remove it, it goes back to its original shape, and you can do this over and over, very typical of shear thinning behavior. So the reason we chose these particular materials is not just because they form a shear thinning material, but also because of their biocompatibility and hemostatic properties. So we do want the blood to basically form a blood clot inside these blood vessels rapidly. So this is an example where you can put the blood in a dish and wait to see how long it takes for it to form a blood clot, which you can see here by the red color, because after you wash it away, it stays. And what you see is that as you basically put the blood in the dish, it takes a few minutes. When you have just the gelatin composition, it still takes a few minutes. Now, as as you start adding more of this nanoclay, you very rapidly get this coagulation, and this clotting times decrease significantly as you start increasing this concentration. Now, when we try to make medical materials, it's very important to be able to test these for a range of different applications. For example, be able to test them for biocompatibility. So we can actually put these materials inside rodents and then look at the inflammation response. And what we see with our compositions is that at early stage, you get a typical inflammation response that's associated with basically the immune cells trying to come and infiltrate and see what's going on. And what happens over time is that you basically get the material degrading, cells kind of infiltrated and deposit their own kind of matrix. And this is very much better response than what you get with other hemostats, like this is a commercially available quick clot that takes a basically very persistent, makes a very persistent inflammation response. Now, when you want to push this through the regulatory, then you start not only biocompatibility, but testing these in small animals. This is an example of a blood vessel that in rodents, this is basically the artery that feeds the leg. We can basically deposit the material inside this artery. We can image it. And when you look at the flow, you see that initially there's a lot of flow, but once you put the material, the flow stops. Now, it seems to work in small blood vessels, but what about human-sized blood vessels? So one of the things we can do is that we can actually take blood vessels from pigs that actually are the same size as human blood vessels, put it in a dish, attach it to a flow system, and then be able to put the material and see how much flow and pressure you need to be able to dislodge it, because that's something you don't want. You don't want the material to put it inside the blood vessel and it goes and causes strokes and heart attacks and things like that. So what we can see is that the material, if you design it properly, it can withstand many times the venous pressure and multiple times the arterial pressure, so it allows you to have a very good behavior. And what we do after this is we actually test these in large animals. We test these in this case, in pigs, where we can we've done a lot of different experiments with different blood vessels inside these models, but this is a typical example where you see initially the flow here. This is one of the bigger blood vessels in the pigs. And what we can do is that we can take the catheter and deposit the material, and what you see is that the material is basically prevents flow. So this is good, and these are some actual videos that show some of this, if I can get this to work. So it shows basically the dynamic behavior here. So you saw Melania Trump kidney issue. This is a very similar kind of example where initially there's a flow and you want to decrease the flow to this lesion. So you can come in, put the material here, and you see that basically it prevents the flow subsequently. And there's lots of other experiments we can do here. Again, large animal experiments are very important for regulatory approval. So, and some of the things that FDA cares about is safety. So what happens if you put the material inside a blood vessel and you try to see if it stays stable or whether it actually goes downstream and causes other issues. So you can put the material upstream from the lung, and if the material breaks into pieces, then you can actually see it in the lung, actually blocking blood vessels. So we can do these kinds of experiments and see that the blood vessels remain patent and open, and we can see that over time, what happens is that the kind of response that we want, the blood vessel remains plugged, it doesn't open up, which is something we don't want. And what happens as cells infiltrate this material, they degrade it, and they deposit their own matrix, causing a response that is typical of the kind of behaviors that we want in a permanent occlusion. So this is an example, and as you can see, it came from an idea to materials development to trying to push it all the way to a large animal, and this is now being pushed forward in a commercial entity. So the other story that I thought would be good to talk about is work related to 3D printing and fabrication, which is, I know is very relevant to this community, and how it can be used for building artificial tissue. So tissue engineering has become more and more important because there's a lot of medical problems where if you have basically a tissue replacement, you can potentially deal with that medical therapeutic. So as a therapeutic. So one of the things that we know about tissues is that tissues are not just packs of cells. Every tissue has a very particular architecture at the microscale. So the way the cells and the different cell types and the vascularization and the matrix all come together is very well organized, and it's very tissue specific. So if you want to have a chance of building tissues, it's very important to appreciate this structure and then be able to mimic it. So one of the things that we've been trying to do for many years is to take inspiration from nature and then develop ways in which we can use technologies and materials to build these tissues. So over the years, there's been a lot of different approaches that we and other people have been working on. These include, of course, things like making porous scaffolds, using lithographic and molding approaches, using microfluidics to develop systems and encapsulate cells, and other things. And more recently, techniques like 3D bioprinting have become more relevant for doing these kind of work. This is, yeah, so that's what happens when you connect the sound. So I'll try to be quick with this, but the idea here is that you can try to fabricate structures, not just by printing cells and materials, but also you can print sacrificial features. So here you can print a material that generates the internal structure of the blood vessel, put your cells around it, get rid of the material to generate the porosity, and you can engineer this in different shapes. You can encapsulate cells around it, and you can put endothelial cells, blood vessel cells that line it and make it more biomimetic and flow liquids through it. Now, the whole idea with all of these kinds of processes is that cells are the ultimate tissue engineers. So you create the environment for the cells to reorganize and form functional structures. And this is really what we do in most of our processes, is that we allow the cells to reorganize over time and make more and more functional structures that have better and better tissue properties. Now, there is a particular areas that of need in this field that we've been really interested in trying to address. One is to try to develop better materials that can be used for printing, so being able to print with better inks. The other things are to deal with things like resolution and throughput of these systems, and finally being able to print with different types of materials. So I'm not going to talk too much about this, but there's a lot of materials and kind of innovations that can be applied to this system, because as you print your kind of materials, you want them to be compatible with printing of cells and many other things. So we've actually developed a series of inks that are basically now commercialized. Some of them are simple inks that are basically made from gelatin and other types of cross-linkable systems. There are universal inks that we've been developing, and also conductive inks. And for today, I'm going to basically not talk about them, but talk about some of the other innovations that we've been trying to push forward. And really that, some of this innovation comes in the form of trying to build systems that can print not just one material, but really enable the printing of many different types of materials. So this multi-material printing is something that the field has been trying to deal with. And a few years ago, we started to think about this kinds of problems. And one of the first inspirations that we got was from a spider. And what a spider does is fairly interesting in that it actually generates different types of silks. And the way it does that is that it has a number of different glands in its back that it can basically mix in different ways to get the spider silk that it wants of a particular type of property. Now you can get this inspiration and be able to build with that kind of approach. So here you see different microfluidic channels. Each one of them has a different color, signifying a different type of material. And the little white circles on top of each one is basically a computer-controlled valve. So by using pneumatics, we can basically pinch off these channels by increasing the air pressure in an overlying chamber here, and be able to open and close these valves. So we can basically program which one of these channels gets expressed and gets extruded through the system. So just to show you how this thing works, imagine if you have 3 different channels, shown here by the 3 different colors, signifying 3 different types of materials, and you first open one, then the second, then the third, then what gets extruded will be these materials sequentially. Now, if you open all of them at the same time, they will all be expressed in the same region of this channel, and what this will allow you to do is have very fine control of the kinds of materials that you're extruding. You can get more fancy with your engineering design. You can, for example, if you have the same 3 channels, you can not only change the material, but also you can change the topography by opening multiple channels at the same time. You can create other ways of controlling surface features. You can have multi-phase systems like encapsulating air bubbles, oil droplets, cells, and other things inside these systems. Now, why we want to do this is a few different reasons. One is that we can use these to deliver cells and materials in the body through little pinholes. Instead of getting major surgeries, you can have little pinholes and then be able to deliver the right types of things inside the body. So these are some examples where you actually have these fibers that are encapsulated with different cells. So particular regions can have one cell type, other regions can have different cell type, and yet in the third regions, you can have these kinds of multi-encapsulated cell types, where in the core here you have one cell type, and in this periphery you have a different type of cell type. And why we do these kinds of structures, for example, is that because the intimate interaction between these 2 different cell types is important. As shown here, these liver cells and the support cells wind up living better when they're together compared to when they're alone. And also you can do other things. You can actually have these fibers signal the surrounding biology. So imagine that you have particular regions in these fibers where you can have molecules coming out and directing the surrounding cells to migrate towards particular regions and not other ones. And these are the kind of stuff that allows us to create new types of therapeutics. Now, it doesn't take too much really insight from that work to try to put these upstream from XY stages and start using this for multi-material printing. And these are some examples where you can actually have different types of materials, again shown with the different colors here, all coming out through the same nozzle, and we can control which one is expressed in different layers or even in the same layer of a 3D printed structure, both of these materials being expressed. Now, you can even go further with this. So this is an example of a multi-material printer that uses the same concept of how, let's say, the 3 primary colors are used to generate all the colors that we see in our surroundings. We can use the same kind of principles to be able to mix different components to generate literally thousands of different combinations of materials that can come out of the same nozzle. And the way that works is, of course, is you can have the different reservoirs, and then you can control which one of these are expressed at the same time, and you can even have mixers inside these nozzles so that as they come out, they can even be mixed together and generate a particular combination of eggs. So why we care about these kinds of things is because it addresses a couple major bottlenecks in the current multi-material printing schematics. And one is that it basically eliminates the need for dead time. So typically what happens is that when you print something, you have to change nozzles and print another layer. And maybe that's okay for some materials, but if you're trying to print biological things like cells, that's not something what you want. So this actually makes the printing process much faster. The other thing is that, as I've shown in the previous slide, you can actually have much more tunable and higher capability printers where you can actually print many different types of materials. And that's also another advantage. So these are the kinds of stuff that we've been pushing forward, and now we're building different types of systems with this. I think there's a lot of interesting kind of opportunities. So what I showed here was a nozzle-based printer. And for some of the people who are familiar with the field, you know that there's different categories of printers, but the same kind of principles can be applied to different types. So stereolithography is a major type of printer. These digital micromirror arrays where you can basically shine a light of a particular pattern onto a surface and then be able to cross-link the material of a particular shape. So we can actually, this is a typical process, but now we can apply our multi-material processes upstream from this, so we can actually change materials that come on this plane and be able to, as basically print with one kind of shape and then bring a different material and then be able to print another type of material very rapidly. So be able to have multi-material printing with these kinds of not only nozzle-based printing but also stereolithographic type systems. So I am at 26 minutes, so I will leave some time for question, but I just wanted to kind of tell you that there are particular common themes. We're very much interested in enabling personalized and precision medicine by using engineering approaches. And typically when you think about precision medicine, you think of this concept that you basically have a patient, you can get a biopsy and then profile, use sequencing approaches and be able to identify the right drugs. And I think this is true, but it's a very limited version of what the capabilities are with this precision medicine area. Right now there's a lot of work in using personalized cells and personalized implants. There's work on trying to recreate human physiology for particular patients and then be able to understand what drugs may be relevant. There's work on trying to use different types of cells, patient-specific and patient-responsive materials, and also devices that can, again, sense and deliver to individual patients. So with that, I'll just wrap the talk and thank the funding sources, our group, and this is the kind of meetings that we have in my lab where literally every single person has a different background, and we kind of sit down and we work through different problems and we brainstorm about them, and I think that's what makes an ecosystem like here exciting. So with that, I'll be happy to answer any questions, and thank you for your attention. I think there's a mic or mics.
Thank you for a great talk. Any questions? You can either use the mic there or go and pass the mic.
And I can also repeat the question if someone is too shy to walk.
So it's a very exciting talk. Case. You have talked about a lot of design principles, but how do you choose the materials? So what is the principle? Mix the 5 things together to be together. And
yeah.
so how do you account for the hydrophobicity? Because all these spiders, whatever is proper, I think they are highly hydrophobic, and they have a tendency to stretch many times rather than getting the way you are squeezing. Okay, just I would like to know about this. If you could kindly explain.
Sure, great question. So we choose our materials based on what the biology and the cells like the most. So, for example, actually most of the cells we deal with, they like a hydrophilic environment. So we use the principle of spiders and silk, which is mostly hydrophobic type interactions. Then we actually, in that reservoirs, we put gels or gel precursors. And as we deposit them, we cross-link the gels. And what these gels allow us to do is to keep the cells in a hydrated environment. And then what we can do with the different types of things that I showed with the different materials is that we can regulate this gel behavior, so we have different types of biological molecules that the cells like around them. So that's, we adopt that process for a hydrophilic system, basically. Yes.
Let's take another
Yes, thank you very much, Professor Khademhosseini. And just now, I just interested to the to your printed microfiber. So, what is the minimum width of your printed fiber? Because is it so? Can it achieve to some hundreds of nanometers? So because so if it is achieved to the nano level width, it will go deeper into maybe the inside of the cells and to do more things. And how to think about this and what is the progress? Thank you.
Excellent question. So the fibers that I showed often have cells encapsulated inside them, and for that reason, we really didn't want them to get much smaller than 10 microns, which is the width of the cells that we have. Now, what we have also done is that we've taken the same principles without cells and put it upstream from electrospinning devices. And in that case, of course, you can get nanoscale fibers coming out. And the way you incorporate cells with those structures is that you can then, first you make the structure and then you put the cells on top. And we do see a lot of interesting correlations between both the chemistry of the materials as well as the architecture and mechanical properties of the materials and of those fibers and how they affect the cells as well. So there's a lot of different things that play with that.
Thank you. Thank you.